Hi, and welcome again to my Physics Online video lecture series. In today's video, we're going to be introducing magnetic fields by way of looking at how they interact with charged particles. At this point in the semester, we are moving from essentially the electricity part of the course to the magnetic part of the course. And then we will sort of combine the two into electromagnetism. So up to this point, we've done electrostatics and a little bit of electrodynamics by way of current and circuits. Now we're doing essentially magnetostatics, and very quickly we'll get into magnetodynamics, which is going to bring us back to electric fields, and yeah, stay tuned. So maybe a brief review. You'll recall that we have already defined the electric field as basically being a vector field which gives you at each point in space the amount of force which would be applied to a charge per unit charge. Again, anywhere in space. So the definition, in some sense, comes from this equation that the E field force is defined as the charge times the E field. In similar way, we had the gravity field, which largely kind of slipped under the radar for most of you. But the gravity field is little g. And so little g gave us the force per unit mass. So you could say something like the gravitational force is equal to the mass of the particle times the g field strength, where g near the surface of the Earth has a value of 9.8. And in these contexts, we could say it's 9.8 meters per second squared, but similarly, we can also say that it is 9.8 newtons per kilogram, just as we could say that the electric field strength is some number, let's say 100 newtons per coulomb, or we could say that it is 100 volts per meter. Both are valid. So with that in mind, let's now consider the magnetic field. So the magnetic field is, we will be using a B to represent it, and it's defined much as these equations up here can kind of define the E field and define the G field. The magnetic field can be defined by the force that it exerts on a charged particle, but unlike these other two definitions where we simply have force equals relevant term times field, this one actually gets defined by way of a cross product. So you have a moving charge, you have the velocity, so it's charge times velocity crossed with magnetic field. So this actually defines our magnetic field, and so now we kind of have to review what is the cross product doing. So let's rewrite that equation. FB is equal to QV cross with B. We need to define for ourselves a couple of vectors. So on the one hand, I have a vector for the velocity, or maybe for the charge and the velocity combined. And then on the other hand, I maybe have a vector for the magnetic field. So the cross product takes into account the angle between these two vectors as well as their magnitudes. The magnitude of this cross product, FB, would be the magnitude of the first vector, which is charge times speed, times the magnitude of the second vector, which is magnetic field strength, times the sine of the angle theta that's between the two of them. The other property of cross products that we need to note is that this means that the magnetic field force, the force from the field, is perpendicular to the velocity, and also that the force from the magnetic field is perpendicular to the magnetic field itself. Remember that cross products are always perpendicular to their constituent vectors. Another thing that could be noted, I should have maybe noted this over here, is the units for the magnetic field. And the magnitude of the magnetic field, the MKS unit is the Tesla, and so we use a T for Tesla. The CGS unit is the Gauss, which we use a G for, and basically we can say that there are 10 to the minus 4 Tesla to 1 Gauss. Why would we use the Gauss? Because the Earth's magnetic field, for example, is about 0.5 Gauss. It varies from maybe about a little over 0.4 to a little under 0.6 Gauss, depending upon where on the Earth's surface you are. This also means that the magnetic field strength from the Earth is about 5 times 10 to the minus 5 Tesla. So Gauss gives you a good estimate in terms of things like the Earth's magnetic field. Tesla gives you the actual MKS unit. You use that if you want to find forces in newtons, in which case you also need to have charge in coulombs and speed in meters per second. In other words, we could say that the magnetic field force is 1 Newton if you have 1 Coulomb moving at 1 meter per second perpendicular to a 1 Tesla field. So in that sense, some sense, that's also your first example. Second thing that we have to note about this charge moving in a magnetic field is how to actually fully determine the direction. So we know that it's going to be perpendicular to the velocity vector. We know it's going to be perpendicular to the magnetic field vector. If these two vectors are both in the plane of the screen that you're looking at, then perpendicular is one of two directions. You can have the field pointing out. So this is out of screen or page or board or whatever. You can have them pointing in. So this would be into screen or page or board or what have you. So we represent out of screen with a dot, into screen with an X, just like an arrow. If you take an arrow and you look at the tip of it, the arrow is pointing towards you. If you look at the tail of it, then you have the tail feathers, which technically make more of a Y shape than an X shape, but it's just easier to quickly draw X's, so we use an X shape. So which one is it if we take this cross product QV cross B? Is it out of the screen or into the screen? Well, for that we use what's called the right-hand rule. So this is my right hand, and there's two ways of doing this rule. One way is to take the finger and point it along the first vector. This is the index finger. And then use your middle finger and pointing it in the direction of the second vector. So if I have Q and V pointing this way, and I have B pointing this way, I'd need to rotate my hand the way it is. And then my thumb, which is pointing towards me, would be the direction in which the cross product points. So you'll have to try that yourself with your own index finger and middle finger. I'll label which one goes where. And again, how do you know which one goes with the index and which one goes with the middle finger? The index finger points along the first vector in the cross product. So this is the first vector in the cross product. So this is first, cross, second. So second vector is B because it's the second one in the cross product. If you reverse the order, then you'll actually get a negative value. And for what it's worth, if some of you out there don't have a right hand, but you do have a left hand, the left hand rule essentially gives you negative values from the right hand rule. So if you use your left hand, you can still figure out the answer. You just have to reverse whatever order you come up with for your thumb. So if I point, here's my right hand. Let's say this is the first vector. Here's the second vector. Here's my right hand. My left hand, in order to rotate to where we're paralleling, would rotate like this, and my thumb is pointing in instead of out. So here's the index, here's the middle finger, thumb, thumb. They're pointing opposite directions. If you have both hands, use your right hand. So yeah, point your index finger along QV, point your middle finger along B. Your thumb will point in the direction of the force vector. Turns out that for this particular cross product, as drawn, you're going to get this for the force vector's direction. So you'll get out of the screen. There is a second version of the right-hand rule that sometimes gets used. What I've shown is what I'd call the Cartesian version. There's also a polar version. And so the polar version, you just kind of use your whole hand. You start off with the fingers pointing in the direction of the first vector, however that needs to be. And then you rotate it around until you can close your fingers to point in the direction of the second vector. And when that happens, your thumb will point in the direction of the cross product. And again, so if I start with my fingers pointing along the QV vector, and then I rotate until my fingers are pointing along the B vector, then my thumb again will point out of the board. So hard to show on the video screen this way though. So I've defined for us what the magnetic field is. I've done some simple force on charged particles. Let's close with a quick example. All right, so we have an example, a 2 Tesla magnetic field exerting a force of half a Newton on a particle whose velocity is 200 meters per second at 30 degrees relative to the magnetic field. We want to know the particle's charge. First step is probably to draw a diagram. Since we're not trying to figure out the directions involved, it doesn't matter in this case whether I draw B at 30 degrees counterclockwise or 30 degrees clockwise from QV, but this is the basic diagram of what's going on. So now I can set up my equation, and just basically using the equation from the previous slide right here, we're trying to solve again for the charge. So we could rewrite this QVB sine theta is FB, and therefore Q is FB over VB sine theta. Plug some numbers in, which I've labeled, of course, up in the paragraph, just so you can see where they're coming from. Plugging all these numbers in, we get Q is 2.5 times 10 to the minus 3 coulombs. So that is our answer. In an algebra-based course, we typically don't use the unit vectors to do our cross products. You can, of course, do cross products in terms of the unit vectors, but I did want to add one more note about the signs and, well, signs as well. So for the most part, our vectors tend to be in the plane of the page you're looking at, and so you would be trying to figure out does the cross product come out of the plane or go into the plane? So one way of thinking of it beyond the right-hand rule is to just ask whether you get a plus or a minus when you take the sign of the angle. So if I'm doing vector A and I'm crossing it with vector B, let's let vector C always be defined as A cross B in that order. Then our angle theta is always, let's say, counterclockwise from A to B. Okay, so I start from A and I go counterclockwise, that's theta. Now we ask, is sine theta greater than 0, less than 0, or equal to 0? Well, if this is true, then cross product is out of page. So this is out of page. If less than 0, then it's into page or screen or what have you. And if it's equal to 0, then C itself has a value of 0. So it basically means you got 0 for the cross product. And so that is another way of looking at the sign conventions for a simple definition. It doesn't hold up as well when you're using unit vectors, and let's say like A has a component along X, along Y, and along Z, and B also has components along X, Y, and Z. And then it's a little bit more tricky to use this. But this does work for an algebra-based course for figuring out what direction is the cross product actually in. So this one right here, cross product would be out of the page at you. So let's consider a few more examples. Okay, so basically what I have here is a whole bunch of different possible A cross B's. And you can use the right-hand rule to get the answer. You can also use this definition of theta as going counterclockwise from A to B in each case, and then basically just take the sign of theta. And in this case, you don't even have to know the actual value of theta, since we're just looking for general directions. Going back to the rules, or going to your calculator, let's put your calculator in degree mode. This angle looks like it's somewhere around 90 degrees. So plug in sine of 85, plug in sine of 97, plug in sine of 91. You'll find that all of those things have positive answers. So in this case, C is out of the page or screen towards you. Okay, next one. Now theta is defined right here, going from A to B. And this right here looks like it's somewhat larger than 90, somewhat smaller than 180. 180 maybe would be along this direction. So we'll call this like a 45 degrees, and therefore this is 135. So plug sine of 135 in. Try sine of 130. Try sine of 128. Sine of 142. Again, in all of these cases, you'll find that you get a positive answer. So again, C is out of the board. Okay, now try this one. Again, we have to go counterclockwise from A to B. So theta is defined by this angle right here. This is pretty close to 90, so going counterclockwise, we get 360 minus 90 is 270. So try plugging 270 degrees or 280, 265, that kind of thing into your calculator with sine. You'll find that in all those cases, C is negative, that you get negative values for the sine. Now try this one. So here's A, here's B. You're going counterclockwise from A to B. That would be like this. Again, this is pretty close to a right angle. So again, you're looking at probably 270 plus or minus 10 degrees. Again, you're getting negative values if you plug those into your calculator. Finally, here's A and here's B. I have to go counterclockwise from A to B. That would be like this for theta. That is somewhere between 270 and 360 total degrees. Let's call it 330 degrees or 320 or 310, 335, that kind of thing. Plug all those into your calculator, and once again, you'll get that the sign is less than 1, and so C is once again into the board, or into the screen, or into the page. So to summarize this previous set of rules, basically, if theta is in the first or second quadrant, so if 0 degrees is less than or equal to theta, which is less than or equal to 180 degrees, then you're going to get out of page. And then if 180 degrees is less than or equal to theta, and I say less than or equal to, I probably should just say less than in both of these cases to keep with our threefold division here. So if this is true, it's into page or screen. And if 0 degrees, 180 degrees, or 360 degrees is equal to theta, then C is 0. Okay, so that's another way of looking at cross products if you have something that's easily defined within your two-dimensional page. And I think that that's it for today's brief introduction video. Thanks for watching, and hopefully you've learned something from it.